We physicists have waited 100 years since 1916 for this photograph.
Deep in the cosmos, where the fabric of reality bends and breaks, black holes have long stood as the universe's greatest enigmas, cosmic titans that devour light itself, hiding their secrets behind an impenetrable veil. For a century, scientists have wrestled with the mystery of what lies at their core, a puzzle where the laws of physics seem to collapse. But now, a revolutionary idea has emerged, shattering our understanding of these celestial giants. A new model suggests that the heart of a black hole isn't a point of infinite destruction but a vibrant, quantum structure, a tangled web of the universe's fundamental threads, holding the secrets of everything it consumes. Has this breakthrough unlocked the key to the cosmos itself, or opened a door to realities we can't yet comprehend? The scientific world is ablaze, and we're only beginning to glimpse the truth. Before we plunge into this mind-bending cosmic revelation, smash that like and subscribe for more awe-inspiring updates from the stars. Black holes have haunted our imagination for generations, described as regions where gravity is so fierce that nothing, not even light, can escape. Traditional theories painted their core as a singularity, a point of infinite density where time and space cease to exist, a dead end for physics itself. This idea, born from the equations of gravity, left a gaping hole in our understanding, a place where our rules broke down. For decades, scientists puzzled over this paradox, unable to peer past the event horizon, the boundary beyond which no information returns. But a new theoretical framework has changed everything, proposing a radical vision of what lies within. At the heart of this breakthrough is a concept that rewrites the black hole story. Instead of a singularity, the model suggests a dense, intricate structure, a quantum fuzzball, woven from the fundamental strings that make up the universe. Picture a cosmic tapestry, not a void but a vibrant sphere of vibrating threads, each humming with the essence of particles and forces. These strings, the building blocks of reality, don't collapse into oblivion but form a complex web, held together by gravity yet alive with quantum information. This isn't a point of destruction, it's a cosmic archive, preserving the history of everything swallowed by the black hole. The model draws from the collision of two great realms of physics, the large-scale world of gravity, where stars and galaxies dance, and the quantum realm, where probabilities rule the subatomic. For years, these realms clashed, creating a paradox that baffled theorists. When matter falls into a black hole, its information, its quantum essence, was thought to vanish, contradicting the principle that information can never be lost. This conflict, known as the information paradox, has tormented scientists for decades. But the new model offers a solution. The information isn't destroyed but encoded within this quantum fuzzball or etched onto the black hole's event horizon, a cosmic ledger preserving every detail of what was consumed. The evidence for this idea comes from cutting-edge data and simulations. Ripples in space-time, detected from the collisions of black holes, carry faint echoes that hint at complex structures within. These echoes, like whispers from beyond the veil, suggest that space-time behaves in exotic ways near the black hole's core, defying the singularity's simplicity. Advanced models, built on theories of fundamental strings, simulate a dense, tangled interior that aligns with these observations. The patterns in the data, subtle yet undeniable, point to a reality where black holes are not endpoints but processors, storing and transforming the universe's information in ways we're only beginning to understand. The scientific community was stunned. This wasn't just a tweak to existing theories, it was a seismic shift, merging the macroscopic pull of gravity with the probabilistic dance of quantum mechanics. The fuzzball model suggests black holes are not destroyers but custodians, holding the quantum imprint of stars, planets, and perhaps even lost civilizations. If true, it redefines what a black hole is. Not a cosmic vacuum, but a vault of information, a bridge between the known universe and the quantum unknown. Could we one day decode this archive, reconstructing the past of entire star systems? The idea feels like science fiction, yet it's grounded in the mathematics of the cosmos. The implications ripple outward. If black holes preserve information, they challenge our notions of loss and finality. Every particle, every photon that falls into their grasp may live on, encoded in a quantum web. This suggests a universe where nothing truly vanishes, where the stories of ancient stars persist in the heart of these cosmic giants. It also opens wild possibilities. If black holes are quantum structures, could they connect to other realms, other universes, perhaps? The model hints at dimensions folded within their cores, realms governed by rules we can't yet fathom. Are black holes gateways, not graves? The discovery has ignited a frenzy among theorists. Simulations are being refined, drawing on data from cosmic collisions and the faint outlines of black holes' boundaries. These efforts aim to map the quantum structures within, testing whether the fuzzball model holds. Some propose that the radiation emitted by black holes, once thought to be random, might carry traces of this encoded information, a whisper of the past waiting to be decoded. Others speculate about traversable pathways, cosmic tunnels linking our reality to others. The black hole, once a symbol of mystery, is now a key to unlocking the universe's deepest secrets. The breakthrough challenges our understanding of time itself. Inside a black hole, time may not flow as we know it, becoming spatial, a frozen state where past, present, and future coexist. If the fuzzball holds the moments of everything it consumes, it could be a cosmic time capsule, preserving not just matter, but the history of its journey. This idea stretches our minds. Could we glimpse the universe's earliest moments, or even the echoes of long-lost worlds, by studying these quantum archives? The black hole is no longer a void, it's a story, waiting to be read. The revelation that black holes might harbor quantum fuzzballs, vibrant webs of fundamental strings, has turned these cosmic enigmas from voids of destruction into archives of the universe's history. No longer mere singularities, they could be intricate structures preserving the quantum essence of everything they consume, challenging our understanding of reality itself. This new model, born from the collision of gravity and quantum theory, suggests black holes are not endpoints but gateways, holding secrets that could rewrite the laws of physics. Are they cosmic vaults, storing the stories of lost stars? Or do they connect to realms beyond our own, hidden in their quantum depths? The scientific world is gripped by fervor, racing to decode a discovery that feels like a message from the cosmos itself, urging us to rethink our place among the stars. The fuzzball model is a cosmic game-changer. Picture a black hole's core not as a point of infinite collapse, but as a dense, tangled sphere of vibrating strings, each thread humming with the building blocks of reality. These strings, woven by the universe's fundamental forces, don't obliterate matter but encode it, preserving its quantum information in a complex dance of probabilities. This resolves a decades-old paradox, the clash between gravity's claim that information vanishes and quantum theory's insistence that it endures. The fuzzball suggests information is etched into its structure or the event horizon, a cosmic ledger that holds the blueprint of every star, planet, or particle it has swallowed. Could we one day read this ledger, unlocking the past of entire galaxies? The scientific implications are profound. This model bridges the chasm between the macroscopic world of gravity, where black holes bend space-time, and the microscopic realm of quantum mechanics, where uncertainty reigns. By replacing the singularity with a fuzzball, it offers a path to unify these conflicting theories, a holy grail of physics sought for over a century. The data fueling this breakthrough, ripples from black hole collisions and faint outlines of their boundaries, reveals patterns that defy traditional models. These echoes, like cosmic heartbeats, suggest a vibrant interior where space-time twists in exotic ways, aligning with predictions of a universe built from strings. If true, black holes become not obstacles, but keys to a unified theory of everything. The model's implications stretch further. If black holes preserve information, their radiation, once thought to be a random leak as they slowly evaporate, might carry traces of this encoded history. Imagine a signal, faint yet decipherable, whispering the secrets of ancient stars or long-lost worlds. Scientists are now racing to analyze this radiation, seeking patterns that could confirm the fuzzball's existence. New simulations are being crafted, blending quantum theory with gravitational data to map these hypothetical structures. If we could decode this information, we might reconstruct the cosmic past, peering into moments when the universe was young. What stories lie hidden in these quantum archives? Speculation runs wild about the fuzzball's nature. Could it be a compressed dimension, a pocket of reality governed by quantum rules? Some theorists propose black holes as gateways, their interiors linking to other universes or sectors of a sprawling multiverse. Picture a cosmic tunnel, not a plunge into oblivion, but a pathway to realms where physics operates differently. These ideas, once relegated to science fiction, now find footing in the mathematics of strings and gravity. If black holes are such gateways, could they hold clues to realities beyond our own? The fuzzball model turns these cosmic titans into bridges, connecting our universe to possibilities we can't yet imagine. The global response has been electric. Researchers across fields, astrophysics, quantum mechanics, even philosophy, are uniting to test this model. Observatories are tuning their instruments to capture more collision ripples, hoping to catch further echoes of these quantum structures. Supercomputers hum with simulations, modeling how strings might weave the heart of a black hole. Behind closed doors, debates rage about whether these fuzzballs are natural phenomena or relics of processes we don't yet understand. Publicly, the focus remains on stunning cosmic images, but the real story is a paradigm shift, turning black holes from destroyers into keepers of the universe's memory. Philosophically, this discovery reshapes our cosmic perspective. Black holes, once symbols of loss, now suggest a universe where nothing is truly gone. The idea that every particle, every moment, might persist in a quantum web challenges our sense of finality. It paints a cosmos where continuity reigns, where the stories of stars and worlds live on in the heart of these giants. This isn't just science. It's a profound shift in how we see ourselves, not as fleeting observers, but as part of an information-rich tapestry, woven through the fabric of space-time. Are we connected to the universe in ways we're only beginning to grasp? The cultural impact is seismic. This isn't a distant theory, but a revelation about the nature of reality, sparked by a model that sees black holes as cosmic archivists. It flips our view of the universe from a place of endings to one of preservation, where even the most violent forces hold memories. The idea resonates beyond science, touching art, philosophy, and human curiosity. What does it mean for a black hole to store the essence of lost worlds? Could it hold the echoes of civilizations long vanished? The discovery has ignited imaginations, from labs to living rooms, as we confront a cosmos that feels alive with meaning. The model also redefines time itself. Inside a black hole, time may not flow but exist as a spatial dimension, a frozen state where past and future coexist. If the fuzzball encodes these moments, it becomes a cosmic record, preserving not just matter, but its history. This raises wild questions. Could we glimpse the universe's infancy, or even the traces of ancient intelligence, by studying these structures? The black hole, once a barrier, now feels like a window, offering a view into realms where time and space intertwine in ways we can't yet fathom. The future is charged with possibility. New experiments are being designed to probe black hole radiation, seeking the faint signals that might carry encoded information. Theorists are refining models, exploring whether fuzzballs could connect to other universes or reveal new physics. The discovery has sparked a surge in collaboration, with global institutions uniting to chase this cosmic mystery. If black holes are archives, how many secrets do they hold? If they're gateways, where do they lead? The model has turned a theoretical puzzle into a clarion call, urging us to rethink our science, our tools, and our place in the cosmos. As the echoes of this breakthrough fade, the questions grow louder. Are black holes the universe's memory, preserving every moment of creation? Could they lead to other realities, hidden in their quantum depths? The cosmos, once a realm of mystery, now feels like a story we're only beginning to read. This discovery, a glimpse into the heart of the universe's darkest giants, has changed everything, reminding us that even in the void, there is meaning waiting to be found. If you're as awestruck by this cosmic revelation as we are, smash that like button and subscribe for more updates from the edge of the universe. Leave your comments below and tell us what you think this discovery means. Cosmic archives, multiverse gateways, or a key to reality itself. We want to hear from you. Thank you for joining us on this journey into the unknown, and we'll see you in the next stellar adventure.